Hi, welcome back. We're still talking about the topic of base 2, and today we're going to talk about the hexadecimal base, or base 16. The objectives of this lesson: Introduction to base 16. You will understand the special relation between base 16 and base 2. You will learn about the importance of base 16. And finally, you will recognize when would be a good time to use base 16. Base 16 is called the hexadecimal base, or just hex. Base 16 contains 16 symbols. Those would be the numbers from 0 to 9, and the letters A, B, C, D, E, and F. They don't have to be capitalized. Sometimes people use the lowercase letters to indicate the numbers. Some examples. The number 10 in base 16 actually means 0 times 16 to the 0 plus 1 times 16 to the first. And that equals 16 in base 10, which is not very surprising, where we could actually predict it. As usual, the first 0 here corresponds to this 0, and the 1 digit corresponds to this 1 in the calculation. Another a bit more advanced example, 2a. This number is in base 16. It contains the letter A as one of its digits. So how are we going to calculate its total value? It goes like this: A times 16 to the 0 plus 2 times 16 to the first. Now you must be wondering, what is this A doing in here? Well, this A has the same role as the number 10. We could replace it by 10, so that's what we're going to do. And we get 10 times 16 to the 0 and so on. And eventually we get 42. Usually, numbers in base 16 are marked with a prefix of 0 and then X. And this is mostly done in high-level programming languages. If you were programming in maybe C or Python or Ruby or something similar, then you must have seen this symbol if you ever seen a hexadecimal number being in use. Some examples of such numbers or such representations would be something like 0x10 or 0x2a. Surprisingly, in assembly, this is not the usual notation, the 0x. There is some other notation. Hex to binary. How could we convert a hexadecimal number to a binary number? We could use, as usual, the remainder evaluation method. For example, we want to convert this number, AB1C, in base 16 to base 2. So, we are just going to do the usual. We are going to try to divide by 2 many times and put it on some kind of a table. Here we have 4 tables. At least it looks like 4 tables, but actually you can just regard it as one table. It is just very long, so I split it into 4 tables. This is the first one. You see, we begin here. This is the original number, and we try to divide it by 2 every time. It might seem a bit strange to try to divide a number that is composed of letters to the number 2, but it is mostly usual. This number ends with C, and C is even, so this whole number is even. That's why we have a remainder of 0, because the original number was even. And the result of the division by 2 is this number, 558e. Again, we divide by 2, and we get here the remainder, and here the result of the division, and so on. We just keep on. We can see that the number in the left column is becoming smaller and smaller, and that is because we are dividing it by 2 every time. And we can see some kind of a strange phenomenon here. If we take a spatial look in the first number in every subtable. Every subtable is just part of the full table, and it has only 4 rows. So I marked in red the first number in every such table, and we can see something interesting here. The original number is AB1C. And it seems like the next one is just the original number when we omit the last digit, the last hex digit. Here we can see that C is removed, and we are left with AB and 1. Next, 1 is removed, and we are left with A and B. And next, we are only left with A. There must be some strange relation between base 16 and base 2. If base 2 can actually divide the digits, or maybe we can actually say that base 2 understands something about base 16. We can say that in every small table, the numbers change in a way that is hard to recognize. Like this number AB1C is changed into 558E. This is hard to predict that this one is going to happen. But after 4 steps, if we go 4 steps in this table, we get A, B, and then 1, which is kind of predictable, where it's just the last letter being omitted. In the same way, if we take a look at the second row in this table, if we go 4 steps from here, we will end up here. 1, 2, 3, 4. We end up at 558. And we have the same effect also in this case. The letter E is omitted. So it seems like in every 4 steps, 1 letter is omitted. If we try to concentrate only on the last letter of each number from the first row, we actually can see the original number. We can see the original number, which is A, B, 1, and C, just like written here. Another interesting aspect of this table is that if we take the binary numbers in each of the small tables and write them in this order, just like the arrow shows, for example, for this one, 1, 1, 0, 0, we get that C in base 16 actually equals 1, 1, 0, 0. And 1 in base 16 equals 0, 0, 0, 1 in base 2, and so on. Finally, we'll get this representation in base 2 for the number AB1C. And it seems like these are just exactly those numbers that we have in this orange table. Right? We have this 1010 that goes here, and 1011 which goes here, and so on. It seems like we can just replace every hex digit with 4 bits from the previous table. So we can actually say that base 16 and base 2 get along. And the reason for that is that 2 to the 4 is 16. If you are more interested in this phenomenon, there is a bonus lesson that explains this more rigorously, and I recommend you to look at it. In order to convert a hexadecimal number to a binary number, it is enough to convert every hex digit into its 4 corresponding bits. Another example, let's look at this number, AD5D, in base 16. This time we use the 0x notation. We look at every digit, at every base 16 digit. First look at A, and we get that A equals 10 in base 10, which is 1010 in base 2. The digit D in base 16 equals 13 in base 10, which equals 1101 in base 2. The digit 5 in base 16 equals 5 in base 10, which equals 0101 in base 2. So if we just replace every hexadecimal digit with the corresponding 4 bits, we are going to get this number that we see here. I'm not going to read it this time. So let's just follow to make sure that we understand where those bits came from. So the first A is supposed to be 1010 in base 2, and here we are, we have it 1010. The next one is D, which is 1101, and we have it 1101. The next 4 bits are 5, and we have that 5 equals 0101 in base 2, and that's what we have here. The last part, 1101, is actually something we know. The last hexadecimal digit is D, and we've already found out the 4 bits that correspond to D. We already calculated them here, so we don't have to calculate it again. We just write 1101, and we get this result. Just to make sure that we are right, we can always use the Windows calculator. I remind you that I open it in the programmer view. In the standard view, I don't have all these strange features, and I want them this time. So I press the programmer view, and I check base hex, which means hexadecimal. You see it here. Now I write AD 5D, and I convert it to the binary form. And we get this result, and it seems correct. You too can use the calculator to check some of the numbers you see in this lesson, and also when you do the exercises for the lesson, it will be very useful. Example: convert the number 1011011011 in base 2 to hexadecimal base. This is actually the reverse question regarding what we have seen. This time we want to convert a binary number to a hexadecimal number. So what are we going to do? We already know that every 4 bits represent a hexadecimal digit. So it's just about dividing the number into groups of 4 bits. And we have to begin from the right. If you remember, when we try to convert using the remainder evaluation method, it always begins from the right, and we are going to begin from the right too. And this is how it's going to be. For this number, for example, the number of digits is not divisible by 4, so we have this first quadruple and the second one, and we have this last bit, 1, which is alone. This could happen. The last set of bits might be of size less than 4. Therefore, we could imagine that there are leading zeros. We could just fill in zeros from the beginning. It's not going to change the value of the number, but it is going to be more comfortable to look at. The last set of bits might be of size less than 4. We could imagine that there are leading zeros. So what's the point? The original number, when divided to groups of 4, doesn't look so nice, mostly because of the last group, which is consisted only of 1 bit, and we want everything to be groups of 4. So we can just put in zeros in the beginning of the number, and now all the groups we have are of size 4, which is nicer. Now we can convert every quadruple of bits into 1 hex digit. So for example, in this number, the first quadruple, which is just 1 in base 2, equals 1 in base 16. The next quadruple, 110, equals 6 in base 16. And the last one, 1011 in base 2, equals 11 in base 10, which is the digit B in hexa. We finally get that the original number that we wanted to convert equals 16B. Let's follow the replacement. the first 4 bits are 1, the next 4 bits are 6, and then the last group is B, and we get 1, 6, B in base 16. Bases that get along. The same phenomenon of easy conversion happens for every two bases B and C, where B equals some power of C. For example, C to the D for some D. And all of those numbers must be integers. For example, in base 4, every digit is represented by exactly 2 bits. And in base 8, every digit is represented by exactly 3 bits. That is because 4 equals 2 to the 2, and 8 equals 2 to the 3. Example, convert the number 1317 in octal base, in base 8, to binary. So this time we are going to convert every octal digit into 3 binary digits. The first digit, 1, is going to be converted to 1 in base 2. The second one, 3, will be converted to 1, 1 in base 2. And the third one, 7, is going to be converted to 1, 1, 1 in base 2. So eventually, we get this result. Just to make sure that we understand the replacement of digits, let's look at the original number. 1 is replaced by 0, 0, 1, and we can see it here. Then 3 is replaced by 0, 1, 1. We can see this here. And we have again 1. We already calculated that 1 equals 0, 0, 1 in base 2. So we can just put the same sequence here. And finally we have 7, which is 1, 1, 1 in base 2. And we just put it in the end, in the place where the original 7 digit was. Why would you care about hex or base 16? We talked about it pretty much, and you are going to do some interesting exercises about it. So maybe it's a good time to think why we are doing it at all. The first point is that in order to talk to the processor, you have to understand binary or some kind of something that relates to binary. That is mostly true in assembly programming. If you are going to program in something much high level, like maybe C, C++, or even some language like Python or Ruby, then usually you don't have to know all of this. Maybe in the layer of C and C++, you get more interaction with the actual bits, but when you go higher than that, you usually don't get to have the hexadecimal numbers being seen so often. But if you are going to program in assembly, then it is very important that you understand binary to some extent. Binary numbers could sometimes be too long. This is important. Binary numbers are very comfortable to work with, mostly because they have only two symbols, 0 and 1. It's so simple. However, sometimes they become too long, and mostly because they have so little symbols. They don't have much. Many computers today work with groups of 32 bits or even 64 bits. We haven't seen those kind of large numbers so far, at least not in this course. And it can be very tedious to write all the bits one by one and then check that you didn't have any mistake. It's not nice. It's not nice to write those kind of numbers directly in binary. Hex numbers have more symbols, thus much shorter than their binary equivalent. This is key. Hex numbers really have more symbols, and in the beginning it could be very strange to look at letters and think about them as numbers. However, the hex numbers are usually much shorter. Let's look at an example. Which one is easier to read? This one is the binary equivalent of this hex number. You can read it as dead beef. This one is, at least for me, kind of hard to read. I think the human eye is not good with lots of symbols that look the same and too many of them on the same line. There are no spaces. It's kind of hard to look at. But this one is not very hard to look at. Another important thing regarding hex and binary is that conversion between hex and binary is immediate. We could have seen this a few slides before, that it is so easy to convert. We can just look at every one digit of hex and convert it to corresponding 4 binary digits. It's pretty simple. We don't have to use the complicated methods of dividing many times or doing anything that takes too much thought. If you are experienced, then you just remember the representation of every digit in binary. There are not so many, in fact. There are only 16. So, in fact, conversion is done digit-wise. Some words about the exercises. Mostly about what you are going to see. There are basic conversion exercises in which you will convert numbers from binary to hex and vice versa, and maybe to some other interesting or less interesting bases. Please use a pen and paper to solve it. This is very important. It will make sure that you understand things. I know that you might have a cool calculator, or maybe you know even to program in some other interesting language using the computer, but please use a pen and paper. It will benefit you in the long run to have a strong basis and understanding of all of those numbers and how it feels like to calculate it. However, I do recommend from time to time to use a calculator or even a computer if you want to check your answers. This is important just to make sure that you understand things right and you get the right answers. I remind you that this lesson has a bonus part regarding the rigorous explanation about base 16 and the conversion to binary and vice versa. The fact that every hex digit is equivalent to 4 binary digits. If you are interested, I recommend you to look at it. See you next time.